In the last lecture we discussed about the damped free vibration. We had a model having the inertia component, having the elastic restoring component, also a dashpot having the C component, and of course we said f of t will be set to will be set to 0, and I am measuring the response at the point where the mass is lumped. So we are talking about damped because C is present, free vibration because f of t is absent. So we found out the expression for x of t in the last class, which is e to the power of minus c by 2m of t. We will use as a and b as constants, a cos omega dt plus b sin omega dt. So in the last lecture we have used C1 and C2 one and the same, but I am deliberately using a and b because C1 and C2 may get confused with the damping constant here. Now as usual we have got two unknowns here, a and b. I want to eliminate or evaluate them. I will use initial conditions, and when I know already that C by 2m can be expressed as zeta omega, where zeta is the damping ratio, and of course omega d is given by omega of root of 1 minus zeta square. So I can rewrite this expression as e to the power of minus zeta omega t of a cos omega dt plus b sin omega dt Now let me expand this as a e zeta omega t cos omega dt plus b let me find the first derivative of this. Minus zeta omega a e zeta omega t cos omega dt minus omega d a omega dt sin omega dt minus zeta omega d. So let us use initial condition at t is equal to 0. Let x 0 and x dot of 0 be displacement and velocity respectively. So let us substitute in this equation here at t is equal to 0 x 0 in this equation. I get this as a, and in the second equation I say x dot 0 will be minus zeta omega a plus omega d b, is it not, because the sin term anyway goes away. So minus zeta omega a plus omega d b. Second evaluate b as x dot 0 plus zeta omega x 0 by omega d, substituting for a as x 0. So, now my equation is complete. I can use these values of a and b here. I can write x of t in the complete form if I know the initial velocity and displacement at time t is equal to 0. I know the whole equation. Let us now see what would be the interesting feature of this equation at various t values along the curve. So, the complete equation what I have here is x of t is equal to e to the power of minus zeta omega t x 0 cos omega dt plus x dot 0 plus zeta omega x 0 by omega d of sin omega dt. So, you can have a general inference from this equation. The first inference I can draw from this equation is that since x of t is e to the power of minus, I can say the response is exponentially because it is e power decaying because it is e power minus. So, decaying. So, a typical value of plot, if you try to look at the plot, my t, this is my x of t, and of course this value is x 0, that is the initial displacement I have. Now, let us say I have a point where look at this equation and see, or try to evaluate this equation at different t values along this curve. So, this is an exponential decay, the response keeps on dying down. So, we already know at t is equal to 0, x is nothing but x naught from this equation or from this curve. Of course, this was an initial condition what we have also assumed. Okay. Now, I want to estimate this at t is equal to pi by omega d. You may wonder that how I am picking up this number, okay, very important. So, you can see here the cosine and sine relationship are functions of omega d. If I try to take this value the denominator and introduce pi here, I can see a phase difference between this by eliminating the omega d. Okay, keep on doing it for different values or multiples of pi, treating denominator as omega d, that is pi, 2 pi, 3 pi and so on. See what happens, you will get an interesting conclusion from this. So, I want you to evaluate t is equal to pi by omega d this equation. So, I will start x of pi by omega d, that is x at t is given by e to the power of minus zeta omega pi by omega d. x 0 cos pi, because omega d and omega d will go away, let me put it cos pi, plus x dot 0 plus zeta omega x 0 by omega d sin of pi. And this will give me minus x 0 e to the power of minus zeta omega pi by omega. So, obviously in this figure it is expected that this value is negative, I get it here, okay. It is this value, and of course this point is pi by omega d. Now let us say at t is equal to 2 pi by omega d, a multiple of this, what happens to this equation again? Substitute back and tell me what happens at 2 pi by omega d. So you will get this value as a positive number, which will be x 0 e to the power of minus zeta omega 2 pi by omega t. Is that okay? Is that okay? So what we infer from the successive values of x at t 0, x at t pi by omega d, x at 2 pi by omega d and so on, I am getting alternate peaks, plus minus plus minus plus minus and so on, okay. I get alternate peaks. Alternate peaks in sense positive and negative, is it not? Obviously when you use 3 pi by omega d, you will see that you will get a negative peak again, okay. Secondly, the qualitative decay component of e power minus is maintained, so it decays. Next, the successive peaks are all factors or multiples of x naught, x naught, x naught of something, x naught of something. So they are all multiple of x naughts, okay. That is multiples of initial displacement. They are clear. We may not have to work out further. So if you want me to mark this point, if you want me to mark, let us say this point corresponds to, okay, and so on, keeps going, because positive negative positive negative, you will get successive peaks. The only clue here is you must know why we are augmenting this equation at a multiples of pi by omega t. The reason is, as I said, since the response is cosine and sine function, harmonic function of omega d, I am eliminating it by keeping the denominator. I am introducing a pi as a phase lag, just see how it is happening, that is how it is shifting, okay. I hope there is no confusion here, we are able to get this. Now interestingly, let us look at the ratio of the successive positive peaks or successive negative peaks, let us see what happens, okay. I will remove this. Let us say I call this as x naught, x suffix 0, okay, this is x 0. I call this as x 1, I can call this as x 2, I am sequentially numbering them as positive peaks, can call this as x minus 1, x minus 2, x minus 3 and so on. So, negative indicates they are all negative peaks, positive indicates they are all positive peaks, and the number indicates they are successive peaks. Okay. So, I can rewrite it slightly in a different manner. I will remove this, it is easy for us to understand. Can I remove this? Take away this, it is easy. So, I will say x0 is x0, x1 is e to the power of minus zeta omega 2 pi by omega d of x0. Okay, let me put it here. So, if I try to work out the ratio of the successive peaks, I get this as e to the power of zeta 2 pi omega by omega d. Is that fine? x0 will go away. I take natural log on both sides. This is what we call as logarithmic decrement, is nothing but 2 pi zeta omega by omega d, where omega d is given by omega of root of 1 minus zeta square. Therefore, logarithmic decrement can be, substituting here, 2 pi zeta by root of zeta square. Okay. Let us expand this argument slightly further and see what is the benefit of this whole discussion. I also know that x0 by x1 is nothing but the decrement, successive decrement is 2 pi zeta 1 minus zeta square. Now, e power, e power. Now, we know e power x, if you want to expand in exponential series, it is given by 1 plus x squared by 2 factorial plus x cube by 3 factorial and so on. That is how you expand e power x. Now, e to the power of 2 pi zeta by 1 minus root of zeta square for very small value of zeta can be approximated as e to the power of 2 pi zeta itself. Is it not? 1 minus zeta square will not cause any difference in the denominator. So, now I can expand this and say that x naught by x1 is simply 1 plus 2 pi zeta. I can also write this in a general form. Instead of saying x naught and x1, I can say x n by x n plus 1. I am taking successive peaks. Any successive peak, I can say it is 1 plus 2 pi zeta. Therefore, zeta can be xn plus 1 minus 1 of 1 by 2 pi. So, this will give me interestingly the damping ratio. Now, you may wonder what is an advantage of this damping ratio. Before understanding this, let us try to take another example and use this expression to find zeta. Let us say I have a curve like this. Okay. I am picking values as x0 here and xm here, some peak. Here I am comparing successive peaks. Here I am comparing n number of peaks where n will be equal to 1, 2, 3, 4. I am picking the fourth peak from the reference peak. I want to generalize this equation for zeta. You may wonder why it is necessary, I will show you that. So, if I try to get a plot like this and generalize the expression for obtaining zeta, then zeta can be obtained as 1 by 2 pi m of xn by xn plus m minus 1. So, in the above example here m is 4. Now, let us see what is the application of this. This expression gives me a closed form solution to obtain the damping ratio, which is zeta, is it not? So, closed form. If by any chance I have the response plot as shown in figure 2, let us say figure 2 is this, which is a response plot, typical. It is a typical response plot. If we have a response, this is t, this is x of t. If you have a response plot as shown in figure 2 with me, I know this value, I can pick up any peak down the line, let us say xm, I count the successive peak number, substitute in this equation, I know everything here, I know this, I know this, I know this, I will get zeta. I can also check this zeta by picking, let us say this value with this, picking this value with this, picking this value with this, it will be uniform. Now, what is the advantage of this? Once I have the response plot as shown in figure 2, I can find zeta, what I call quantify zeta. Now, the question is, where will I get this figure 2? Where will I get this figure 2? By any chance, by any magic, if I get this figure 2 directly, can find zeta. Interestingly, my dear, this is the only way to get zeta. You will not be able to get zeta otherwise by any other technique. On the other hand, you must get x of t for a given vibration system experimentally. So, what you do? You simply have a model which is an idealized single degree or multi degree, whatever may be, apply a free vibration to this, put a displacement transducer and accelerometer here, directly record the time history vibration of this mass in a time scale like this. you will know what is the damping imposed on the mass under the given working condition. So, I can obtain this experimentally, and most importantly zeta is worked out only based on free vibration. Okay. So, free vibration tests are very important in dynamics, especially in motion structures, because you will have an idealized model which has wave effect or water body effect surrounding the mass. For example, install a system in the test bed or a wave tank, commission the system, for example maybe a TLP or a spar or a gravity platform or an articulated tower, commission it, do not apply any excitation force from the wave or anything, let their structure remain static at t is equal to 0, apply a free body motion to the mass point and get the response plot. From the response plot you can find the damping imposed on the model by water surrounding the body, material deterioration, all put together. Okay. This is how we can easily obtain the free vibration response, and based on which I will get zeta, and zeta is of course expressed in percentage of what is a ratio, percentage of with respect to critical, talking about underdamped system. So, percentage respect to critical is what we will evaluate. Okay, we can easily get this value. So, in this model we have assumed that C is a viscous damping component, because it is the damping force is proportional to the velocity. Now, if it is not proportional to velocity, let us say for example a Coulomb damping model, let us see what is the great difference between a Coulomb damping model or Coulomb damped response in comparison to viscous damped response as you just now saw. So, the first observation what you understood from a viscous damped response is the response decays exponentially, it means the decay is faster, because exponential decay is always faster than a linear decay, is it not, it is very high. Whereas in Coulomb damping it will be the other way, we will see what is that. Any questions here? Any doubt? Any questions, any difficulty here, because few of you may know this, but still it is important for us to understand in the continuous flow, so that you will remember how we are proceeding. So, I am talking about Coulomb damping more in detail. Okay. We already know the Coulomb damping force is normal force acting on the system multiplied by the coefficient of friction between the two dry surfaces where mu is in contact, n is the normal force. Therefore, we already said this is independent of velocity, it is independent of velocity, but it is a function of time. Okay. Now, most importantly look at this curve here, we agree that the response decay because of the presence of what is that, the response decay because of the presence of damping. It means when I have a body which wants to move to its right, the damping force should move the body to its left. When I have any time instant where the body is moving to its left, the damping force will move the body to its right. And we have very clearly seen here the movement of the body is alternate, somewhere it is moving positive, negative, positive, negative. It means the damping cycle is valid only for half, is it not? After half it changes its sign. Is it clear? So, we cannot simply apply the damping force for the full cycle, because within one full cycle there is change of sign happening in the response. So, we must look only at the half cycle first to capture the qualitative variation of the response occurring because of damping. If you capture the full cycle, you will not know. If you look at only x0 and x1, you possibly thought that the variation was simply like this, you never know it is coming down to negative. When you look at x0, x minus 1 and x1, you will realize that the damping is getting change of sign, I mean the force is getting change of sign also, the response is changing its cycle, right. So, we look at the half cycle. So, I am interested if this is my response, this is my damping force, if this is my response, this is my damping force. That is what we understood from this figure. It means the action of damping is effective only for half cycle, is it not? Then afterward changes the sign. So, let us capture the half cycle response for a Coulomb damped model and see what happens. Any questions here? Is this clear what we are trying to say? This I have inferred only from the figure what I just plotted. Okay. So, let me draw a typical Coulomb response x of t. So, let us call this as initial displacement, I call this as x1, x of minus 1, x of 2, x of minus 2, x of 3 and so on. This is x of t. So, let us select half cycle. So, now I can say if the velocity is 0, okay, you have to draw this curve very carefully, there is no slope here, there is no slope here. So, the velocity is 0. Therefore, change in kinetic energy will be 0 and hence work done by the mass will also be 0. I will remove this. Hence half k x1 minus x minus 1 the whole square minus f damping of x1 minus x minus 1 should be set to 0. So, this is Oh, I am using minus sign, it should be plus. So if we expand this, and this is going to be my FD. Okay. If we expand this, half k x1 minus x minus 1 x1 plus x minus 1 is equal to FD of x1 plus x minus 1. X1 minus x minus 1 is 2 FD by k. So what does it mean? The response reduction within half cycle from x1 to x minus 1. The response reduction within half cycle from x1 to x minus 1 is equal to twice of Fd by k, which is the damping force. If you apply the same algorithm back from x minus 1 to x2, you will again get the same relationship. You can try. On the other hand, x1 to x2, that is the response decay from positive x1 to positive x2, the successive peak is twice of 2 Fd by k, which is 4 Fd by k. So I can really write that the response reduction between the two successive peaks is 4 Fd by k. That is true for negative also, it is true also. So there are some inferences I can draw from this understanding. They are the following. 1, response decays, no doubt, even when you use Coulomb damping, but the decay is linear. Okay, it is a linear number, is it not? And it is constant per cycle. Every cycle of positive, it is only 4d by k. Another cycle again 4d by k. So if you want to really reduce the response from x1 to xn, you have got to undergo so many number of cycles to bring down the response from this peak to the desired value of your choice. Okay. So what do you understand by making so many number of cycles? You are alternately creating a response which will induce a fatigue problem into your model, because the model has to undergo n number of cycles before it reaches the desired response of your level. You want the response not x1, you want the response as xn, let us say here somewhere. Since you know every cycle the response decay is constant for Coulomb damping, you must make the model to undergo that many number of cycles to bring the response from x1 to xn of your choice. Therefore the decay is delayed or slow, and hence it is not desired. Okay, it is not desired one, where it is exponential decay. The decay is exponential, it is linear here, that is very fast. It is linear, but it is exponential, it is very fast. Okay. I have a question for you. When this response will stop decaying? It has to stop somewhere, right? When will it stop decaying from further decay? When the elastic restoring force in the given system is not capable of overcoming and nullifying the damping force, it will stop, is it not? So the shutdown of this is automatic. Right, it will not damp beyond that. Therefore, any damage caused to the elastic component in your structure will affect the damping cycle directly. That is another demerit in this model. Any damage you have caused to the elastic restoring component in your system, or the stiffness weakness or degradation of stiffness in your structure because of some loading phenomena which will happen, I will show you later in the next module of lectures. When your stiffness gets degraded, this will directly affect the damping philosophy or principle in your structure. That is why this kind of damping is not recommended and commonly used for ocean structures. We are not saying whether it is good or bad. There are two important points. One, the decay is there, but it is delayed and slow. You need to undergo certain number of cycles to ensure a specific level of decay. By any chance, if the elastic restoring component K or the stiffness degradation happens in a structure by damage to the structure, it will directly affect the damping relationship of the structure. Just now we saw the damping, the decay will stop when there is an understanding between K and Fd, is it not? That will affect. So, because of these reasons it is not acceptable and commonly used in ocean structures. So, we have learned two things from this class, saying that how to estimate damping for a given structural model. The most common, popular, easy method is experiment. And why we use viscous damping? Okay. So, we have discussed about damped and undamped free vibration models. In the next class we will talk about damped and undamped forced vibration model, where f of t will not be equal to 0. Any questions here? So, all in single degree. Then we will move on to 2 degrees and multi degrees quickly and then find out the characteristics. That is where we will end. The 12th lecture is running, we will finish this module on 18th lecture. We will have 6 more lectures on this module, then I will move on to application of dynamics to ocean structures. I will pick up different models of ocean structures, gravity platforms, spar, TLP, tension articular towers, and then triceratops. I will show you how dynamic analysis is done for these kinds of models. That will carry around another 15 lectures. Then we will talk about stochastic dynamics in the 3rd module. That is what the program is. The whole program is available in the website of NPTEL of this course. You can download the syllabus and see how we are covering. The first module is for 18 lectures, we have finished 12th lecture today. Any questions? So, thank you.